All right, buddy. Wanted to do another wanted to do another equilibrium problem with you on the inclined plane before tomorrow we get into the idea of the non-equilibrium and what's going to happen there. So the problem I want to do for you is number 7 from the problem set that I gave you in class. It says the coefficient of static friction between a 3 kilogram crate and a 35-degree incline is 0.300. What is the minimum force that must be applied perpendicular to the incline to keep the crate from sliding down? So this problem is asking us about an applied force, right? And that applied force is this one that's in the picture. Things that we know. They told us that the mass of the crate is 3 kilograms. They told us that the angle is 35 degrees. And they told us that the coefficient of static friction is equal to 0.300. Also, keep the crate from sliding down. That means that crate's going to be motionless. So that means we're back to an equilibrium situation where we have net force X and net force Y equal to 0. From that information, we get started on the next part. Now, knowing what we know here, well, let's go and start putting forces on this picture. So there's my picture. Remember we talked about the idea that when we start putting forces on this drawing, first force we're going to put in is going to be our gravitational force. There it is. And because we know how to calculate the force of gravity acting on something, right? It's just the mass times 9.81. We can label that force as 29.43 newtons. We talked about the idea that there is a normal force in this problem, right? That normal force looks like this, perpendicular to the surface. Now, not to be confused, even though I drew it over that arrow that was in the picture, we're also applying a force in this. Ooh, get rid of that. We're also applying a force to this block that looks like this, applying it perpendicular to the ramp. So we're pushing down on that block. From this picture, it also tells us something about static friction. I think we've established the idea right now that static friction, or friction, is going to be up the ramp, because in the case of before we put that red arrow on there, all three of those forces would sort of contribute to moving this block down the ramp. Friction acts opposite of those applied forces, so it's going to be up the ramp. Right now, we only know one of these three forces, right? Or sorry, one of these four forces. Ultimately, we're looking for this purple force, right? We said that was our unknown in this problem. What is the applied force? So we attack this problem the way we've been attacking it, right? We tilt the axes, and hopefully this will turn out good. Not quite as good as I would have liked, but we'll adjust a little bit. Normal force, applied force, like that. Okay. We talked about the idea that if we know this angle, the angle that the ramp makes with the ground, we also know this angle right here. And we also talked about the idea that this gravitational force has components. It has a component this way, and it has a component this way. Now, don't get confused. That solid purple arrow that I've drawn on the drawing is not a component of gravity. That's a separate force. They just so happen to be along the same axis, but it's a separate force. With that being said, we start figuring some things out. Because we know this green triangle, right? We know an angle, we know the hypotenuse, we can figure out the two sides. So go ahead and do that now. And when you do that, you should end up with, let me do this first. Let me move this out of the way. Well, I can move that out of the way. Move this and this, and I'm going to replace it with 24.1 here, and then 16.9 here. What does that do for us? Well, because we know this is an equilibrium situation, these two things have to be true. we've already established that this was a normal force, right? This red force, even though I forgot to label it, we should say is the force of static friction. Now, we're talking about minimums here, blah, 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 blah. So in this case, there is a 16.9 Newton force pulling this block down the ramp, just from the parallel component of gravity. In order to keep that block from moving, the static friction force also has to be 16.9. In this case specifically. But if we're talking about the coefficient of static friction, the formula for the coefficient of static friction is the maximum static friction over the normal force. So if we take and put in things that we know, assuming that this static friction force that we have just calculated is the maximum static friction, we can plug that value in here. They gave us the coefficient of static friction in the front of the problem, so we can figure out how big the normal force would have to be in order to create that much static friction, 16.9 specifically. So if we go back, we find out that our coefficient of static friction was equal to 0.3. Taking it back here, right, 0.3, 16.9 over the normal force, or because I'm like this, .9 over the normal force, we find out that the normal force has to be equal to, let me do this real quick, 56.3. 33333. So we know that in order to create the required static friction force, which from our parallel component of gravity we knew had to be 16.9, the normal force has to be 56.3. Now, taking into account that we have to have equilibrium on the y-axis. If we look at the y-axis in this problem, there are three forces on the y-axis. There's the normal force, there's this perpendicular component of gravity, and then there's the applied force. By pushing down perpendicular to the surface of the ramp, we are increasing the force into the ramp, which then increases the normal force, balancing it out, making equilibrium on the y-axis. If we increase the normal force, we also increase the force of static friction. So by pushing down into the ramp, we increase normal force. By increasing normal force, we increase static friction, and that allows us to hold that block in place longer than if we were just working with gravity and friction between the ramp itself. The point being that this applied force has to balance out the y-axis. So we have 56.3 in the upwards direction on the y-axis, 24.1 already downwards, so the applied force has to be the difference between those two, which turns out to be 24.1, turns out to be 32.2 newtons. So that's how hard we'd have to push down on that block in order to increase the normal force enough to create enough friction to hold that block in place.